Good morning, classmates. Good morning, Dr. Mani Ivyuta. I'm Cynthia Sanico, and I'll be reporting work, energy, and power. So the specific instructional objectives. At the end of the lesson, students should be able to define work and energy, correctly identify work from given situations, describe the different forms of energy, and solve related problems involving work and energy. So what does work mean to you? Are you doing work when lifting weights, walking with a big bag of grocery in your hand, completing your homework assignment, or even writing an essay? Yes or no? Let's find out if your answer is correct. What is considered as work done in physics? That is when you push a heavy shopping trolley for 10 meters, or you lift your school bags upwards by 1 meter. It considered it is considered as work done. So what is not considered as work done? That is when you push against a wall, there is no work done. Jumping continuously on the same spot, and or holding a cat and walking around the classroom. Okay. So work is done only when a constant force applied on an object causes the object to move in the same direction as the force applied. Work is a scalar quantity by Yu DeYoung and Roger A. Friedman, 2008. So it has only magnitude and no direction. According to Jammer Max 1957, the term work was introduced in 1826 by the French mathematician Gaspard Gustave Coriolis Gustave 1829 as weight lifted through a height. According to René Dugas, French engineer and historian, it is to Solomon of Cox that we owe the term work in the sense that it is used in mechanics now. Dugas are 1955. So work is the transfer of energy through motion. In order for work to take place, a force must be exerted through a distance. The amount of work done depends on two things: the amount of force exerted and the distance over which the force is applied. There are two factors to keep in mind when deciding when work is being done. Something has to move, and the motion must be in the direction of the applied force. So work can be calculated by work done is equals to constant force times distance moved in the direction of force, or M. Okay, so work, or W, is equals to force, or F, times distance, or D. The unit of work is joule, and the unit of force is Newton, and the unit of distance is meter. The SI unit of work is the joule, which is named after the 19th century English physicist James Prescott Joule. Problem number 1. You are helping to push your mother's heavy shopping cart with force of 50 Newton for 200 meters. What is amount of work done? So given, we have force and distance, which is force is 50 Newton and the distance is 200 meters. So the formula in finding the work is force times distance. So 50 Newton times 200 meters is equals to 10,000 joule. That is our work. Another problem. Jack put on his backpack of weight 120 Newton. He then starts running on level ground for 100 meters before he started to climb up a ladder up a height of 10 meters. How much work was done? From the physics point of view, no work is done on pack at the level ground here, because the left is perpendicular to movement. Work is done on pack only when Jack climbs up the ladder. So we will disregard this 100 meter. Instead, we will use 100 Newton and 10 meter. So we will solve now for work, which is 100 Newton times 10 meters. So our work is 1,200 joule. Derivation. So work is equals to force times distance. The unit of work is joule, unit of force is Newton, and again, the unit of distance is meter. And the SI base unit of Newton is kilogram meter per second squared times meter. So the SI base units of joule is kilogram meter squared over or per second squared. Okay. Now let's move on to energy. So what is always present but never visible? Of course, it is energy. Although energy isn't visible, you can detect evidence of energy because energy is all around you. You can hear energy as sound, you can see energy as light, and you can feel it as wind. You use energy when you hit a softball, or when you lift your book bag, or compress a string. All living organisms need energy for growth and movement. Okay, so people needs to eat for us to grow. Okay, we need to drink. Okay, what else? We need sunlight. Okay, so those are energy that we need. And also, energy is involved when a bird flies, a bomb explodes, rain falls from the sky, and electricity flows in a wire. So what is energy? That it can be involved in so many different activities. Energy can be defined as the ability to do work. If an object or organism does work, which exerts a force over a distance to move an object, then the object or organism uses energy. Because of the direct connection between energy and work, energy is measured in the same unit as work, which is joules. In addition to using energy to do work, objects gain energy because work is being done on them. So we have two sources of energy, renewable and non-renewable. So when we say renewable sources, these are the source of energy that is natural, like solar or our sun, water, wind. Those are some natural resources or the renewable resources. And when we say non-renewable resources, these are resources which are limitadora. Okay, so these resources are not natural resources. Okay. So, forms of energy. Everything exists or ceases to exist because of its presence or absence of energy. It is stored in different forms and can transfer or transform. Energy can be also transferred without being transformed, or it can also be transformed without being transferred. And also, it can be transformed during transfers. So these are the forms of energy. We have radiant, electrical, chemical, sound energy, thermal energy, nuclear, mechanical, and magnetic. So as I search through the internet, I encounter this Mr. Sense strategy. So this strategy helps us remember the forms of energy. Mr. Sense, M stands for mechanical, R radiant, C for chemical, E for electrical, N for nuclear, T for thermal, and S is for sound. So Mr. Sense. Those are the forms of energy. Mechanical energy is when work is done to an object, it requires energy. And the energy it acquires is known as mechanical energy. These are the energy that moves objects from place to place. So example for mechanical energy is when you kick a football, you give mechanical energy to the football to make it move. So nganong mudagan man ang nganong mo lupad man ang kuan, ang bola, it's because of you imo nanggi, because when you kick the football, you give the energy to the football. Okay. And when you throw a bowling ball, you give it energy. So the bowling ball nagka-gain sa energy, that's why move ang ball. Okay. So mechanical energy falls under two categories: potential or kinetic energy, or yes. So when we say potential energy, this energy is energy in matter due to arrangements of its parts, its composition, location, and structure. It is commonly considered as a stored energy. It is okay. So the various forms of potential energy, we have gravitational, chemical, elastic, electrical, or nuclear. And when we say kinetic energy, these are energy in moving matter and wave. Some forms of kinetic energy are motion, radiant, sound, thermal, and wave. Mechanical work done when equated to changes in the mechanical energies resulted to operational definitions of kinetic and potential energy in the following equations. So in finding the potential energy, we have potential energy due to gravity. So the formula here is mass times acceleration due to gravity times height. And another formula is potential energy, elastic potential energy is equals to 1/2 of spring constant and compression or extension length squared. So for kinetic energy, we have 1/2 times mass times velocity squared. Kinetic energy exists whenever an object which has mass is in motion with some velocity. Everything you see moving about has kinetic energy. The kinetic energy of an object in this case is given by the relation. So we have 1/2 or 0.5 mass times velocity squared. Okay, so the greater the mass or velocity of a moving object, the more kinetic it has. So which do you think of these two transportation has or possess greatest kinetic energy? So of course it is the bigger one. The one that has a greater mass or velocity. Okay. Potential energy exists whenever an object which has mass has a position within a force field. The most everyday example of this is the position of objects in the Earth's gravitational field. The potential energy of an object in this case is given by the relation potential energy due to gravity, or gravitational potential energy, is equals to mass times acceleration due to gravity times height. Okay. So potential energy that is dependent on height is called gravitational potential energy. Example, a waterfall, a suspension bridge, and a falling snowflake all have gravitational potential energy. Now if you stand on a 3-meter diving board, you have 3 times the GPE than you had on 1-meter diving board. GPE stands for gravitational potential energy. So the bigger they are, the harder they fall. It's not just a saying, but it is true. Objects with more mass have greater GPE. The formula to find GPE is weight times height. So another form of energy is the light or radiant energy. This is the energy that can move through empty space. The sun and stars are powerful sources of radiant energy. The light given off by light bulbs, campfires are also forms of radiant energy. So chemical energy, this is the energy released by a chemical reaction. The food you ate contains chemical energy that is released when you digest your meal. Wood, coal, gasoline, and natural gas are fuels that contain chemical energy. Another form of energy is electrical energy. This is the energy that comes from the electrons within atoms. It can be generated at a power plant or inside a battery and can power everything from remote-controlled cars to refrigerators. Lightning and static electricity are also forms of electrical energy. Nuclear energy contained in the nucleus of an atom. And nuclear energy is released when nuclei are split apart into several pieces or when they are combined to form a single larger nucleus. Heat or thermal energy. It is the energy created by the motion of atoms and molecules that occurs within an object. So thermal energy exists when you heat a pot of water on a stove. So example, that's it. So the last form is sound energy. Sound energy is the movement molecules in the air that produces vibrations. Alarms, music, speech, ultrasound, medical equipment all use sound energy. VCR tapes change sound energy into electrical energy. The electrical energy records the sound using magnetic tape. Speakers read the magnetic tape and change it back into sound. So conversion of energy, it is the transformation of energy, or it is a process that involves energy change from one form to another. So example, in changing forms of energy, an automobile engine changes chemical energy to mechanical and heat energy. Another example of energy transformation is a tree changes radiant energy to chemical energy. Hammering a nail changes mechanical energy to deformation and heat energy. And a thermonuclear reaction changes nuclear energy to radiant and heat energy. An electric mixer changes electrical energy to mechanical and heat energy. And the last is a lamp changes electrical energy to radiant and heat energy. So from this stored chemical energy, it transforms to light energy. So conservation of energy. The law of conservation of energy states that the total energy of an isolated system remains constant. It is said to be conserved over time by Richard Feynman, 1970. This law, first proposed and tested by Emily Du Châtelet, means that energy can neither be created nor destroyed. Rather, it can only be transformed or transferred from one form to another. So, let's solve some problems. Problem number 1. Renata Gas is out with her friends. Misfortune occurs and Renata and her friends find themselves getting a workout. They apply a cumulative force of 1018 newtons to push the car 218 meters to the nearest fuel station. Determine the work done on the car. So, we have force, which is 1018 newton, and distance, which is 218 meter. So, we are going to determine the work done on the car. Solution. Work is equals to force times distance. So, 1018 newtons times 218 meter is equals to 235,440 joules, or 2.35 times 10 to the power of 5 joules. Problem number 2. A car with a mass of 700 kilograms is moving with a speed of 20 meters per second. Calculate the kinetic energy of the car. So, what is the formula in finding the kinetic energy? It is the 1/2 times mass times velocity squared. Okay. So, we have mass 700 kilograms. We have velocity 20 meters per second. Substitute the 0.5 or 1/2 times 700 kilograms times 20 meters per second squared. So 20 times 20 meters squared seconds squared. Okay, so the answer is 140,000 kilogram meters squared per second squared, or 1.4 times 10 to the power of 5 joules. Problem number 3. An object of mass 2 kg is taken to a height 5 meters from the ground. The acceleration due to gravity is 10 meters per second squared. Calculate the potential energy stored in the object. So given mass is 2 kg, acceleration due to gravity is 10 meters per second squared. Potential energy is missing. Okay, so we will calculate the potential energy. Solution. So what is the formula in finding the potential energy? It is the mass times acceleration due to gravity times height. So this is the symbol for potential energy, or U. Okay. So 2 times 10 times 5 is 100 joule. So that is the potential energy stored in the object, 100 joule. Activity. Okay, so this will be your activity for this lesson. Just follow the direction. Read first the key concepts and follow the direction. Okay, so or the procedure. Then you have here the guide questions. I'll be posting a copy of your learning activity later. So these are the references, and that ends my report. Thank you.